All right. Good evening, everyone, and welcome to the first session of the Fundamentals of Particle Physics program. We are very excited to be starting this program as it's been in works for quite a while now. It was started by the Particle Physics Demystified session that we at Nucleus created with the help of Dr. Arindam and Dr. Kenji from Shivnada University. And it's very overwhelming that so many of you registered and were curious enough to learn more about particle physics along with us. So, without further ado, let me introduce your tutors for this session. Um, my name is Uday, and I'm a graduate from Shivnada School, Noida. And I'm accompanied by Pantho Chakrabarti, who's a physics student from Shivnada University, and Devangi Agarwal, who is also a physics major from Shivnada University. Uh, Devangi, would you like to add something?
Hi everyone, I'm Devangi, and as Uday said, I'm a physics major from Shivnada University, and I'm also the secretary for the Physics Society. Okay, so now we would be beginning the session shortly. Before we begin the session, I would like to inform you all a little bit about the instructions. So, we would be having 2 classes per week, as we already mentioned in the mail earlier. So, one class would be like live on YouTube, like it is right now, and the other class would be an interactive session on the Microsoft Teams. And you would be getting the mails regularly with the links in it. And so you'll get the link before the session, and we would like to thank Dr. Arindam and Dr. Kenji for helping us in this, and Rachna ma'am and Vinita ma'am from Team Nucleus who helped us in structuring the entire program.
Thank you so much for that, Devangi. And we now start off the session. Today we'll be focusing on the fundamentals of particle physics, along with a brief history of the atomic theory. So we have planned for you a general introduction to what you'll be learning in the following weeks, along with the other historic session that should get you interested in the nitty-gritties of the subject that we're trying to cover in the entire program. So I'll now start the presentation. First of all, I'd like to discuss what particle physics is. Now, if you go up to a particle physicist, they would probably tell you that they are studying the fundamental particles that make up the universe as we know it. So the word particle really implies something that's very small. It's something. It's a word that we have come across for since we're children. But in particle physics, we're trying to study the very minute particles that constitute everything that we see in our lives. For example, a lot of you may be aware of the term atom, which was thought of as the basic building block of everything that we observe in the universe. However, scientists did more work and they found out that there are other particles that are involved in creating what we know and what we see around us, which is what particle physics is. So the word fundamental particle basically implies that these particles that we're studying in particle physics are not made up of anything else. They are the smallest constituents in the universe. So, in simpler words, we're just trying to say that they are the smallest things possible. They cannot be divided furthermore. And that is what particle physics is really about. Sometimes this field is also referred to as high energy physics because of some complicated reasons that we'll probably encounter later in the session. And when we're studying particle physics, we're basically trying to understand the universe around us at the smallest possible scales. And we use a lot of experiments. For example, a major experiment in the field of particle physics is the one at CERN. You might have heard of the Large Hadron Collider, which is a very big project in the field of physics that is situated at CERN in Switzerland, which scientists use to try to study particles and their behavior. Along with that, there are also many theoretical implications of particle physics. For example, scientists are constantly trying to find the theory of everything, or something that helps us explain everything that exists in the universe, which is also a very important part of particle physics. And that's what makes this field so beautiful, because scientists are constantly trying to work with theories and experiments and trying to merge these two together in order to create a broader understanding about the universe. So, in this session and in this program as well, we'll be giving you the introduction to this rather dynamic field. We'll be talking about various concepts that are at the center of particle physics, and along with that, we'll also be discussing some more exciting implications of particle physics. For example, astroparticle physics, where we'll also be discussing topics such as dark matter and dark energy that are extensions of this field known as particle physics. And right now, I'll hand it over to Pantho, who will start us off on the journey about the atomic.
Okay, so the whole concept of particles arose from a simple question. What happens if we keep cutting something in half over and over again? Can we do that indefinitely, or is there a limit to it? And as you'll see in the next few slides, it is a really it is an age-old question. Next slide. Okay, so first we'll start here in 600 BC India. Acharya Kannada. He founded one of the 6 schools of ancient philosophy called Vaisheshik. One of them we all know is yoga. The sage simply put forth the idea that the atoms or anu are eternal objects which makes up fire, water, earth, and air. Human living beings are excluded from his atomic theory. He believed that these atoms are infinite and motionless and indivisible. Next slide. Okay, so now we go to ancient Greece. Go to the ancient Greeks, the birthplace of Western philosophy. Democritus's atomic theory stated that the universe is composed of 2 elements, the atoms and the void in which they exist and move in. His version of atoms were indestructible, solid but invisible, and they were also homogeneous. Instead of going the elemental route, he went more of the physical properties route. So he believed that solids, the atoms of solids are made of small pointy atoms so that they can stick together and hold in place. And for liquids, they're made of large round balls which can flow easily. Next slide. Uh, can you hear me?
Yes, you're audible.
Uh, it's still on the Democritus slide.
Oh, there seems to be a delay because I've already changed the
Okay.
slide.
Yeah, okay, it's
Let
changed
me
now.
just restart the presentation.
No,
All right.
yeah, it's okay now.
Okay, got it.
Yeah, sorry for the technical difficulties. Okay, so 76 years later, we get Aristotle. Even though he was one of the first scientists who documented and experimented on different things, his version of the atomic theory was even more primitive than his predecessor. He believed that there are just 5 elements, baseless and formless, and there are no such things as atoms, and everything is made up of these elements. Cool. Okay, next slide. Okay, so enough of history and philosophy. Now we get to real science. You may have noticed there's a huge time jump between Aristotle and John Dalton. He was in 386 BC, and now we are at 1844 AD. This huge jump is because science is a slow process. It takes years and decades to develop and prove any kind of theory. So before Dalton came the alchemists, who were just chemistry with a bit of magic, the periodic table, and the creation of chemistry as a field. According to his model, matter is composed of extremely small particles called atoms. His atoms were indivisible and indestructible, and atoms of a specific elements were identical to each other, and atoms of different elements were different from each other. So combinations of the chemical compounds were formed from the combination of different kind of elements. Next.
Discovery. William Crookes discovered cathode rays when he was studying electrical discharge in gases, whereas J.J. Thomson discovered that the cathode ray consists of negatively charged particles called electrons. Production. Cathode rays are produced in a discharge tube. Hence, the discharge tube is generally referred to as the cathode ray tube. The cathode ray tube is a partially evacuated glass tube with cathode and anode placed at the ends of the tube. A vacuum pump is used to partially evacuate the tube. The cathode is connected to the power source with the help of a clip. The tube is supported on a stand. It was found that electric discharge through gases took place only when the pressure inside the tube is lowered and the potential difference between the electrodes was high. To produce cathode rays, high potential difference of 10 kV to 20 kV is applied between the electrodes and the pressure is reduced to 0.0001 millimeter of mercury by means of a vacuum pump. A glow is seen on the walls of the glass tube. The bright fluorescence glow is due to the striking of the rays emitted by the cathode. These rays are cathode rays. Properties of cathode rays. Cathode rays travel in straight lines. When an opaque object is placed in the path of the cathode rays, a shadow is cast on the glass wall opposite to the cathode. This shows that cathode rays travel in straight lines.
Okay, so what you saw was an experiment that we needed for the next breakthrough in the atomic model. I'll be showing a simulation to show what cathode rays are. And just give me a minute. Okay, is my screen visible?
Yes.
Okay, so if I display the particles, so basically the particles originate from the cathode and they move through the anode and they move through this tube. So if we increase the charge on the plates, we see that these particles move towards the positively charged plate. This proved that whatever is in that are whatever consists of these beams, they are negatively charged. So and then there were this magnetic field. Similarly, in presence of a magnetic field, you can see how the beam slowly moves towards the magnet, and if you flip the magnet, it goes down, like it moves down. So with this similar with this experiment, J.J. Thomson proved that this beam is made up of negatively charged particles. So that's how the first subatomic particle, the electron, was discovered. Okay, I'll be and Uday, take over for the presentation. Okay, so now we reach the J.J. Thomson's atomic model. As you saw earlier, he discovered the electrons, and so Dalton's model was a neutral model. So now to incorporate the results of the cathode ray tube, Thomson changed his model so that a sphere or positive charge ball. So this model is also appetizing names such as watermelon, choco chip, and plum pudding model. Over to you, Devangi.
Okay, so moving on to the next model, we have the Rutherford model. Now, this model is a bit more advanced and it is more closer to the model that we know today. So, in this model, we have a nucleus at the center and electrons surrounding it. So now Rutherford proposed this model through a experiment known as gold foil experiment. So first we'll watch a video of the experiment and then I will explain more later. Udai, can you play the video? The audio is not coming in the video. Can you check that?
Yeah, sorry about that. It should be audible now.
Shown here is the diagrammatic view of the famous gold foil experiment conducted by Lord Rutherford. The radioactive source, rich in alpha particles, was kept in a thick lead block with a narrow opening. The alpha particles were confined to a narrow beam by passing them through a lead sheet with a slit. An extremely thin foil of gold was bombarded with these fast-moving alpha particles. The scattered alpha particles were detected using a rotatable detector, which has a microscope and is screen-coated with zinc sulfide. The whole experimental setup was placed in an evacuated chamber to prevent scattering by the air molecules. These striking particles caused scintillations on the screen. Based on the observations, Lord Rutherford deduced these conclusions. As most of the alpha particles pass through the gold foil without any deflection, most of the space within the atoms is empty. As some of the alpha particles were deflected by large angles, they must have approached some positively charged region responsible for the deflection. This positively charged region is called the nucleus. As very few alpha particles experienced the deflection, it was concluded that the volume occupied by the nucleus is very small. Since alpha particles, which are comparatively denser, were deflected by the nucleus, it shows that almost the complete mass of the atom must be within the nucleus.
Okay, I would show a simulation regarding the same. Is my screen visible?
Yeah, it's visible.
Yeah.
Okay, so as you can see, this is the nucleus, which is made up of protons and the neutrons. And we have 79 protons and 118 neutrons right now. And these are the positively charged alpha particles. And this is the entire nuclear scale. So now if I start the simulation, you can see that these alpha particles are, some of them are going in straight lines, some of them are getting deflected, and some of them are even bouncing back. So if we reduce the number of protons, if we reduce the number of protons and the neutrons, that means the size of the alpha particle, the size of the nucleus decreased. And now if we again bombard the atom with the alpha particles, we see that more of the alpha particles are going in straight lines. So from this we can conclude that there is a positively charged particle in the nucleus, which are the protons, and neutrons would be the neutral particles, that is with no charge. Aditya, can you share the presentation? So we have these 4 results from the experiment. So as we know that most of the alpha particles just pass through the atom, which says that most of the space within the atom is empty. And since some of the alpha particles were deflected by a certain angle, that means that the positively charged nucleus is not distributed uniformly, but it is just at the center and it occupies a very small volume. And since some of the alpha particles got deflected by 180-degree, and those were like very little, like hardly 2 or 3 alpha particles, which shows that the volume of the nucleus is very small as compared to the entire atom. So this was the gold foil experiment and the atomic model proposed by Rutherford. So now moving on to the next one, we have the Bose atomic model. So in the Bose atomic model, Bose said that the electrons move around the nucleus in a very similar manner, such as planets move around the sun. So we all know that planets move around the sun in fixed orbits, and in a very similar manner, electrons also move around the sun, move around the nucleus in fixed orbits. And these fixed orbits have some constant energy, and so every orbit is associated with a particular energy, and the orbit which is like nearer to the nucleus has is like in a lower energy state than the other orbits. So when an electron, if it gains any amount of energy from outside, it goes to a higher orbit, and then it is called an excited orbit. That means it has got into an excited state. And when that electron loses its energy and goes back to its original orbit, that is the original state that was in, it gives off some radiations. So this was the atomic model that Bohr has proposed. And now moving on to the last atomic model, which we have accepted most, is the electron cloud model. Now this model is very similar to the Bohr model, but there are no distinct energy states. So from the quantum theory, it was found that the electrons and other particles as well can behave both as a particle and a wave. So if something behaves as a wave, it means it has a wave nature and it has a wavelength. And if something behaves as a particle, that means it has a particular momentum. Therefore, particles can have both waves, wavelength and momentum. And due to this, electrons were not found in distinct orbits either. They had their position was thought of as a cloud with some particular kind of energy, and this is the model that is accepted the most. Over to you then.
Thanks a lot, Devangi. So we discussed the electron cloud model at the end, which, as Devangi mentioned, is the current accepted model of the atom. But what we're doing here, as it is the particle physics program, we want to go beyond that. We want to go beyond the idea of just an atom, right? And this is the same thought that scientists had about 100 years back, where after discovering the electrons, protons, and neutrons, and after discovering what an atom is, scientists began to wonder further that are these particles really the smallest things that can exist? And they began to wonder whether there can be particles and there can be manifestations in the universe that are even smaller than protons and neutrons and electrons. And to their surprise, they found out that it was in fact true. They found out that there are particles that exist in the universe that are much smaller in scale than these protons and neutrons that they had discovered earlier. And this is where particle physics as a field really came into existence. It came through questioning the true nature and the true composition of protons and neutrons. And along with that, scientists also pondered upon different questions, such as they started wondering whether light is made up of particles as well. Because when we look at light, we don't really imagine what it's made up of, right? Because it seems like a ray to us, which behaves sometimes like a particle, sometimes like a wave. So scientists really began to wonder whether light too is made up of some sort of a particle, where particle physics really came in and they figured that out, and that particle is now called a photon. We'll talk more about that in the consequent sessions. And along with that, scientists really began to wonder how things in the universe really take place. common question that they had was, how do forces exist in the universe? How is anything affecting anything else in the universe? Is it pure magic, or are other particles responsible for it? And scientists have a tendency to not believe in magic. They try to find out logical reasoning for things that they observe, and that's what particle physicists did. And that's where they found out about more particles that exist in the universe that are much smaller, again, than protons and neutrons, and they incorporated that into particle physics as well. And that's what the essence of particle physics is. Now, I would like to talk about the Standard Model. The Standard Model is something that you might have heard of recently or in the past. It is a very common. It's a very common attribute of particle physics, and it's right at the center of the subject that we're trying to study, because the Standard Model really talks about the nature of all the particles, and it's essentially a catalog of all the fundamental particles that exist in the universe. So, as I mentioned earlier, in the early 1900s and in the mid 1900s, scientists were trying to figure out what the universe is made of, and they discovered a lot of new particles. For example, as I mentioned, they discovered that protons and neutrons aren't the smallest particles, and they're made up of smaller particles known as quarks, and they discovered these particles. Then they also discovered the photon, which I also mentioned, which is the light carrying particle, and they discovered a bunch of new particles during this era in science. And finally, in 1975, there were a bunch of scientists who decided that we need to make this field more systematic. They said that, okay, we've discovered a bunch of new particles and they tell us about how different things behave, how different things exist, but we need to look at it in a more organized manner. In the same way, you might have heard of the periodic table, where scientists looked at all the elements that they had discovered and created, and they wanted to put them in a table that would allow them to look at it in a more systematic manner. In a similar way, physicists wanted to do the same for the particles as well, and that is when the Standard Model came into existence. The term Standard Model was first used in 1975 to give a name to this collection of particles that had been discovered and confirmed by science, and that is what the Standard Model is. To give you a bit more detail about the subject, on the right you can see this image of the Standard Model. It contains all the particles that we know yet that have been discovered by physicists. And the Standard Model essentially contains 4 types of particles. These particles are called quarks, leptons, gauge bosons, and scalar bosons. These are very fancy sounding words which may or may not make any sense to you, but I promise they will as we go on. So the Standard Model is basically divided into these 4 categories of particles. Quarks are responsible for, as I mentioned earlier, the existence of protons and neutrons. For example, a proton is made up of 2 up quarks and 1 down quark, and a neutron is made up of 2 down quarks and 1 up quark. And these compositions also give protons and neutrons their very specific properties. For example, in the case of a proton, as Devangi and Panthu explained earlier, protons have a positive charge of +1, and that is because of its composition. As it turns out, the addition of 2 up quarks and 1 down quark leads to the proton acquiring a charge of positive +1, which is why proton behaves in the way that it does. And it also allowed us to discover the proton in the first place. So all these fundamental particles really interact with each other in different ways. They collide with each other and give rise to more complex particles. They interact with other particles and give rise to new forces and give rise to properties in the particles such as mass and charge, as I mentioned earlier. And all in all, these fundamental particles are responsible for the universe as we know it. So we'll go into the details of the Standard Model in the next class, which will be an interactive session. So we'll be talking more about what these 4 families of particles really are and how they interact with each other. We'll be talking more about the details of the interactions and why we divided the Standard Model into 4 parts in the first place. And we'll also be talking about the future prospects of the Standard Model and whether we think that the Standard Model is complete, or are we still looking for more particles. So that's where I would want to leave you as of now, with a brief introduction of what the Standard Model is and what we know about the particles, about the fundamental particles in the physics community at the moment. Um, I'll just stop presenting my screen very quickly. Yes, thank you so much. Now, I just want to remind you that as we have time left, we're looking forward to taking more questions in the chat. If any of you are watching on YouTube Live right now, we'll be happy to answer any questions that you may have. Devangi or Panther, do you want to add anything in conclusion?
No, no, I think there's nothing to add now. We'll just have to
If
take it then.
anyone has any questions, please let us know. Or if you want, if you don't have any questions right now, you can always write to us and we can help you out.
Right. And I just want to remind everyone that the next session will be an interactive session. So everyone who signed up for the workshop will be invited to a meeting of which the link would be sent to you via email, and you would be able to interact with all of us live as we continue the program. And along with that, if you have any questions later on as well, you can feel free to write to us, and we'll be happy to answer them now or in the session later on. And I hope that you learned something new during this session, and I hope that you're looking forward to joining the next one. Thank you so much.
Oh, I think someone asked a question, what are leptons and bosons? So we will be talking more about the particles of the Standard Model in the upcoming sessions. So we have a different module for that, so you will know them in a while. If there's any question related to whatever we talked about, any of the atomic theories, you can ask us right now.
Can I just add here one line?
Yes, of course, ma'am.
It's very interesting to see that you guys have made such good presentation and doing peer tutoring for rest students who are registered. Uh, now, can I, Devangi, just add one line about lepton so that uh, obviously you will be covering that topic later on, but still, can I just add one line here about leptons? So, students, you just see that when these peer tutors are talking about protons and neutrons and electrons, and we all have done that when we were in class, junior class, we read that these are the fundamental particles, these are the smallest particles. But as these your tutors start going ahead with the course, you will be surprised that they are not. They are not the smallest particle of the element. So when you talk about leptons or quarks or all these all these ingredients which make neutron, proton, electrons, um, that will be then you will understand that how physics grow. Like when you are in class second or third, you see that you come to know that atoms are like building blocks of element, or class 4 or 5 you learn that atoms are actually making that, and you may not be knowing about electron, protons, neutrons. You come to the bigger class and you come to know about electrons, protons, neutrons, which actually have made atom, right? And as you go further bigger class, you will come to know that these electrons, protons, neutrons are also made up of some ingredients. So those ingredients your tutors will be talking in next class, and they will be making a very clear picture of that what electron, protons, and neutrons are made up of. And there they will discuss about leptons and quarks. Am I right, Pantu?
Yes, ma'am. So we have got a few more questions.
Yeah.
About can quarks be split into smaller particles still? Uh, in short, as of now, no. As of now, quarks are indeed fundamental particles. So as of now, we can't split quarks into smaller particles. And do quarks have an electric charge? Again, yeah, they have electric charge. as electrons and protons are considered to be considered to have +1 and -1 charges. Quarks, the electric charge of quarks are in fractions. Like for example, the up quark is +2/3 charge, and the down quark is -1/3 charge. We'll cover more of these in the next sessions, so stay tuned for that.
Is there any more questions on YouTube? You people have made it so clear, um, but still, they can also mail questions to you. Am I right, Uday, Devangi, and Pantha? They
You
have
can write-
your
Can-
Yes, ma'am. Sure, ma'am.
So over to you, Uday, Devangi, and Pantho. Any last line, if there is no questions of this session, and what homework you are giving to these kids, what to explore more, what to come prepared with. So please tell them. Thank you.
I think for today's session, as it was the first session, we unanimously decided to not give the kids any solid homework because we have been student and we still are students. So I don't think I would have been very happy to get homework for the first session. Uh, but I think I would just request everyone to just try to read more about what we studied today and try to explore a bit on their own about what the atomic theory is and what the standard model is, so they can be prepared for the next class. And I would just say that the other homework is just feel free to write to us if you have any questions and don't hesitate to ask.
And stay curious always.
All right, I think we can end on that note if we don't have any more questions coming on YouTube.
Naman, over to you.
All right, thank you.